Recording. Okay, great. So basically, our today's colloquium speaker is Professor Jayant Murthy. He is a senior professor and is a former director of Indian Institute of Astrophysics in Bangalore. So Professor Murthy had done his PhD from Johns Hopkins University in USA. He worked for GSFC NASA. Then he was also a research scientist at Johns Hopkins University in USA. As per professional organizations, he is part of International Astronomical Union. He is president of Commission of 21. He is also part of organizing committee division 9th and 11th. He is part of American Astronomical Society and obviously Indian Astronomical Society of India. Yes. His research is mainly based on space missions, like he's interested in his interstellar dust, diffuse radiation, and obviously hardware development for the space instrumentation. He's also involved balloon-based instrumentation related to UV-based astronomy. And he was a key part of, he is the key part of UVIT calibration team, UVIT onboard astrosat. And today he will be talking about diffuse ultraviolet and visible light from our galaxy and beyond. So I will not waste much time. I will invite Professor Jayant Murthy to talk on his colloquium. Thank you, Professor.
Okay, thank you, Sunil. So being introduced as the former director is certainly better than being introduced as the late director, which I have been in the past, sort of reminding me of Monty Python and the parrot. But anyway, what I will be talking about is the diffuse background, almost entirely in the ultraviolet, but just a little bit in the visible at the end. And I always found the historical context to be quite interesting. As Sunil said, I was the president of IAU Commission 21 before the reorganization. In fact, I was president when it was dissolved. So you might say I presided over the demise of IAU Commission 21. And this was called Light of the Night Sky. And so when it began in 1955, the focus was on the International Cooperation for Atmospheric Observations. And this thing included the Soviet observations. So at the time, the light of the night sky meant largely air glow, the atmospheric emission. But then what happened was that space-based observations came up, and with space-based observations, you started looking at more than just the atmospheric emission. And then there was a sociological shift in the field, in that the atmospheric people shifted from being part of the astronomical community to being part of the space physics and geophysics community. So the light of the night sky, that commission still existed, but it shifted over to Zodiacal Light. And then after that, it went to the diffuse galactic light and the extragalactic background light. And so as Tanabe, who was one of the past presidents, said, the light of the night sky, when you're trying to extract the background, what you're really looking at is a number of different components, all the way from the dark count of the instrument to air glow, to interplanetary light, the zodiacal light, to galactic light. If your instrument has large enough pixels, you'll get integrated starlight. Then you get the dust scattered light, the diffuse galactic light, which may include emission lines, it may include molecular hydrogen, all sorts of stuff. And then finally, you get out to the extragalactic background light. But even though you're looking at all of these different components, they're all mixed together. And so breaking them up into the different components, you really have to understand the distribution and the origin of the different components for over the entire field. And so finally, again, as reflecting the change in the field, the Commission 21, Light of the Night Sky, it shifted out of the solar system group and shifted into galactic into the galactic whatever division of the IAU. So we shifted to galactic and extragalactic backgrounds. And then when the reorganization came, then that's when the commission ended. So just a few definitions. What am I talking about? So this is DGL, the diffuse galactic light, diffuse extragalactic light. So that means not stars. So any place there's a star, I can't observe. I have to block out that region around the star. The UV part of the galactic light is from about 100 angstroms to maybe 3000 or 3200 angstroms. Of course, the edges, you can shift it a little bit this way, that way, depending on what you're talking about. And then you have the visible part, which is from 3200 to 10,000 angstroms. And so as I said, I'll focus on the UV part. And the UV part largely means 912 to 3200 angstroms. The part below 912 angstroms is difficult to observe because of the Lyman limit. Any photons below 912 angstroms will go to ionized hydrogen and will essentially be lost from our field, from our line of sight. And once you get to the visible, then you're competing with the solar light. I'll talk about this a little more later. So the technological problems get more difficult. Now, the units, because we're looking in the UV, the units we use are photon units. That is photons per centimeter squared per second per steradian per angstrom. And these are actually natural units for us because we're working with macho photons in the UV. So we detect each photon, or at least we detect each photon with whatever the efficiency is. And so really we are counting photons, and our statistics are photon statistics. Just to convert this into units that other people may be familiar with, it's 1.33 times 10 to the minus 11 ergs per centimeter squared per steradian per angstrom at 1500 angstroms. And if I convert it into nanowatts per meter squared per steradian, which is sort of the SI unit, then it's pretty easy. 100 of my photon units is equal to 2 nanowatts per meter squared per steradian, regardless of wavelength. Now, when I gave this talk at the IAU colloquium on galactic and extragalactic backgrounds, I went specially prepared with this conversion. So I looked up how many nanowatts per meter squared per steradian it was, only to find that everyone there uses magnitudes per square arc second. And this is a difficult thing for me because I don't even know what a magnitude per square arc second is in the UV. Typically, magnitudes use Vega and A0 star, but an A0 star has no flux in the UV. So how do you calculate magnitudes in the UV? And the people who do, I don't know, all sorts of different ways. But anyway, photon units is the preferred unit for us. Now, the sources are all nicely encapsulated in this old picture from the UVX experiment. The idea behind this was that in the early days of looking at the UV background, there was a big conflict between our group at Johns Hopkins and Stu Boyer's group at Berkeley. And so what some bright person at NASA headquarters said, okay, let's give both of them an experiment on the space shuttle so that they look at the same regions, and then hopefully they'll get the same answers. So they did that, and this was the UVX experiment, ultraviolet experiment. This was the time when the space shuttle was supposed to be the do everything for NASA. All science was going to be shifted to the space shuttle. Everything was going to be taken up by the shuttle. It was going to be much cheaper than sending things up by rockets. As it turned out, they perhaps underestimated the difficulty and the cost of a space shuttle flight. So what this, you may or may not be able to see my cursor, but what this shows is the UV from or our two UV instruments. We had two spectrographs. This is a far ultraviolet spectrograph on this side and a near ultraviolet spectrograph on this side. And so what I mean by far ultraviolet in this context is from 1200 to 1800 angstroms. The reason that specific wavelength is it's defined by the technology. This is a cesium iodide photocathode, and the cesium iodide photocathode is sensitive up to 1800 angstroms. The work function goes out at 1800 angstroms. And the short wavelength end is defined by a magnesium fluoride. I'm sorry, in this case, it was a calcium fluoride filter. And then this is the long wavelength instrument from about 1800 angstroms to 3200 angstroms. We took a wavelength at a time. So this is, each line is a single spectrum in the FUV and the NUV. And time goes from dusk to dawn. So what we see is Lyman alpha here. Lyman alpha is always the brightest thing in the sky. And when you're looking with a diffuse instrument, Lyman alpha is always going to dominate your field. So anything close to Lyman alpha, you have a very difficult time observing. For instruments that observe longward of Lyman alpha, you can put in a calcium fluoride filter, which will get rid of most of it. You can also put in a barium fluoride filter, as Galax did, which will get rid of these oxygen lines. This is 1304, and this is 1356 angstroms. And again, you can see the dawn to dusk terminator, and you see that there's very little emission at around local midnight. In the NUV, you see these stars going through, that's these lines going through, that's continuum emission from stars. You don't see very much of it in the FUV, because most stars are so cool that A stars, for instance, A stars will die out around 2000 angstroms, no flux below that. As you go to longer wavelengths, you start to see zodiacal light come in. And zodiacal light is, of course, sunlight scattered from interplanetary dust. And that will start to cut in at about maybe 2500 angstroms or so. And so as you go to longer wavelengths, you start to pick up the zodiacal light. Over here, as you get close to dawn, now you pick up these nitric oxide lines from the atmosphere. We had a short connection. We had a short in the connector for the NUV detector. So you see there's more background. The FUV detector, very little background. And this is true of most UV detectors, very low dark count. Because we had this short in the NUV detector, there was a higher instrumental background. And so basically I've just cataloged the sources here. Instrumental background, that's a dark count. Air glow, you see the lines. Zodiacal light, which is sunlight scattered by interplanetary dust. Unresolved stars, that's these stars here. Diffuse galactic light, which is dust or emission lines, and then extragalactic light. Now, the UV background actually started very early, long before the X-ray background, for instance. So it started in the late 60s with the Japanese experiment, Hayakawa et al., and then Lilly and Witt. And then it continued on with OAO2, the Orbiting Astronomical Observatory, the second one. But the problem was that most of these experiments had all been intended for stellar observations. And so they had a small field of view and a variable dark count. And if you didn't do your corrections properly, your background would be all over the place. And then there were a bunch of rocket flights from Hopkins and from Berkeley, which culminated in a couple of review papers in 1991 by Stu Boyer and Dick Henry. Unfortunately, these observations didn't agree very well. And so there was always some controversy about the diffuse background. And the main reason is because the diffuse background, if you're looking at the diffuse background, you're looking down at the level of dark noise. We're looking, typically we talk about signal to noise of 1, 2. If we get signal to noise of 3, we're very happy. So way down at the dark noise level. And so the early experiments were just difficult to use. So so when the first experiments other than these rocket experiments came from Voyager, and I'll bring Fuse in here also. So Voyager, the Voyager 1 and 2 were both launched in 1977 to explore the outer planets. But of course, there was a long cruise phase before the outer planets, in between the planets, and then again after the planets. And so most missions, what they do is they just turn the instrument off in that time. But for Voyager, primarily because of Jay Holberg and Ron Allen, they included a cruise phase in which they made astrophysical observations. And they, in fact, opened it up for proposers. And so we managed to get a fair number of observations. And even more than that, because people were looking in this wavelength range, that is the 912 to 1200 angstrom wavelength range for the first time, people tried to look at objects that just weren't visible in that range. So we got a lot of Voyager observations, all the way up from about 1.3 AU or so, all the way out to about I think about 50 AU was the last observations. They turned the instruments that we used, the ultraviolet spectrographs, UVS, they turned those off now to save power. And now I think the only things that are operating are the magnetometer and some plasma physics measurements. So that's why every couple of years or so you get this big press release saying that Voyager has reached the edge of the solar system. Now, the only other instrument which has observed in this wavelength range was Fuse. And Fuse was actually intended for high resolution spectroscopy. The primary scientific goals were the D to H ratio and searching for O6 absorption in the sky. But it turns out that if the regions were bright enough, we could use it as a low resolution photometer and get decent observations of the far UV sky. And just to show you the quality of the data, this is the Voyager data here. So the Voyager instrument went all the way from 500 angstroms to about 1700 angstroms, but the sensitivity was much lower at longer wavelengths because they wanted to suppress the long wavelength emission. They were more interested in the short wavelength emission. And so, and as you look at planets, they wanted to cut down the signal there. And so what we're trying to observe is the emission in this range here from 600, or from 900 to about to 1200 angstroms. And in that range, you have Lyman alpha here, and you have Lyman beta there. The resolution of Voyager was about 30 or 40 angstroms. So you had very few pixels in the short wavelength range. So your limits were not so great. I've left these in instrumental units so that you can see the noise. And finally, what we get is what we were able to say is that we were able to put limits of about 100 of our photon units. I'll try to put that in context later. So that was Voyager. The real revolution in studying the diffuse UV background came from GALEX. And GALEX, the Galaxy Evolution Explorer, again, not intended for a study of the diffuse background. It was intended for galaxy evolution. GALEX itself was launched by a Pegasus from an L1011. The L1011 took it up to some altitude, dropped the Pegasus, and then the Pegasus ignited and took it up into low Earth orbit. An earlier Pegasus had failed the instrument. I think the payload didn't separate properly, but GALEX worked perfectly and went up. And so what Galax did is it observed the sky from 2003 to 2013, about a decade. And there were a number of different classes of observations. There was an all-sky imaging survey, the AIS, where they observed as much of the sky as they could, but with a exposure time of only 100 seconds. And then the what's it called, the medium imaging survey, if I remember right, and that was about 1,000 to 1,500 seconds. And then the deep imaging survey, which were exposure times of 30,000 seconds to as much as I think the biggest was, or the longest was close to 100,000 seconds. And now, because Galax was in near Earth orbit, the or low Earth orbit, the exposure times themselves, they could only observe at orbital night, because Galax was a microchannel plate detector. It had a UV photocathode with channeled through a microchannel plate into a delay line detector from Aussie Sigmund. But they were worried about the total charge that comes through the microchannel plate. So that means that they could only observe in orbital night. Because if you remember the plot I showed, the air glow increased dramatically, including Lyman alpha. It increases dramatically as you get into daylight. So they only observed at local night, between about 8 o'clock and 8 o'clock at night and 4 o'clock in the morning, plus midnight plus minus 4 hours. And so these very long observations of 30,000 seconds, or anything longer than about 1,200 seconds, the orbit itself at this altitude, about 600 kilometers, is 90 minutes. And so of that 90 minutes, you only have about 20 minutes of actual dark time observation. And so in order not to saturate the detectors, in order not to damage the MCPs, they limited the observations to within plus minus 4 hours of midnight. And so these very long observations were made up of a series of visits, and this will become important later, made up of a number of visits where each visit was 1,000 seconds or so. And so here's the coverage of the sky. Most of the sky was covered with 100-second observations. A few were covered with much longer observations, typically things that other people had observed. The Virgo cluster, the Virgo cluster, there was anyway, a number of these observations that other air fields that other people had observed. Subaru, I think, was one. The FUV detector failed early on in the mission, I think in about 2007 or 8. And so they avoided the galactic plane early in the mission because they were worried that the galactic plane is too bright. And so it was only near the end of the mission when they said, okay, anyway, we've lasted this long, we'll go ahead and try to observe the galactic plane. And so there were some galactic, some NUV observations in the galactic plane, NUV observations of the Magellanic Clouds, but no FUV observations because the FUV detector had failed by the time they went onto it. And just to show you, just to illustrate how dark the UV sky really is, and for those of you used to optical images, this may be a bit of a surprise. This is the FUV, and you see there's only one star here, maybe a star here, maybe a star here, maybe a star here, only a handful of stars. And even if you get to the NUV, there's still very few stars. So typically, if I look at an entire field, no more than 10 to 15% of the total signal in that field is from starlight. Everything else you see is from diffuse background. So if you want to look really deep into the sky, the UV is the place, because there's no competing terrestrial, or there's no competing, I mean, the sky is just dark if you go into the UV. So what I did was that once the Galax data were more or less complete, I took all of the Galax data. Now, the Galax data themselves are at about are 1.5 arc second pixels. The resolution of the instrument was about 5 arc seconds. But in practice, I can't get the diffuse background to this level. There's just too much instrumental noise or too much noise to get it down to this level. So what I did was I took all of the data that were available, and this was about almost 45,000 observations, and I broke it up into the visits. The reason I broke it up into visits is because each visit might have been taken at a different time and a different date and different ecliptic coordinates. So the zodiacal light and the air glow were all different from visit to visit. I would expect that the diffuse background and the extragalactic light would not be different, but certainly the local background, the air glow and the zodiacal light might be different from each. And so then I blanked out stars in each visit. So if I go back to this field here, I would just put a square around each star and just leave that out. Square was hopefully broad enough that I didn't include any of the PSF from the star. But even otherwise, the stars, as I said, 10% in the FUV and maybe 30% in the NUV. And then I binned these fields into 2 arc minute resolution. So I took the 5 arc second Galax resolution and I binned it into 2 arc minute pixels. So now, because I was primarily interested in the galactic and the extragalactic background, I wanted to get rid of the air glow and the zodiacal light. So what I did was I took a plot of, I took each of the individual visits. That was a total of 76,000 exposures. And I took not the Galax field, but one of the engineering detectors, the total event counter measurement. And I just plotted it as a function of local time. Now, for those of you who may be planning to launch spacecraft in the future, and they refused to do it for UVIT, I told them to and they refused to do it, it's important to map the local time of the spacecraft. So what I had to do was I had to go back to this space track where they track the the 3 line elements of each of the spacecraft at given times, and then you convert those 3 line elements into quaternions. No one knows what a quaternion is, but then finally you get you find out where the spacecraft is on the Earth, and then you can convert that into local time. So it took me about 3-4 months to do that. It would have been much easier if they had actually kept track of the time. But anyway, I finally did that. And so here is a plot of the signal as a function of the local time. And these are, I think, 90% contours, if I remember right. And so you see that the signal tracks very nicely with zenith angle, with the time from, I'm sorry, not with zenith angle, but with time from the local midnight. And so at midnight, it's pretty low. If in fact within plus minus 1 hour of midnight, there's pretty much nothing. Even if you go far away, it only goes up to about 50 of my photon units. And in fact, if you integrate over an entire observation, over the entire time from -4 to +4, this only works out to about 20 or 30 photon units of signal. So that's the air glow. And what I did was I parameterized this and I subtracted the air glow from every observation. Now the zodiacal light, because this is light from the sun, it cuts out by about 2,000, 2,500 angstroms. And so there's no contribution from the zodiacal light in the FUV. There's only a contribution in the NUV. And so if I plot the signal as a function of ecliptic latitude, you get this very nice curve where there's where the signal is greater at close to the ecliptic plane. And it worked out that this followed the visible observations. So what people have done is from the Canary Islands, they mapped the zodiacal light across the sky in the optical. And so the UV zodiacal light matches the optical very, very tightly, but with a slope of about 0.65 of the optical. And so if you're speaking naively, that tells you that the grain albedo of the interplanetary grains is 0.65 that of the visible. So now when we take all of this and put it together, I'll start with the Voyager and Fuse observations. And so this is not a uniform coverage of the sky. When we got targeted observations with Voyager, we looked at specific regions. And one of them was the coal sack here. But other people look for other things. And so basically it's a serendipitous survey of the sky. And the same thing with Fuse. Fuse, in fact, was even more serendipitous because what they did was they looked for stars. And so what we looked, because Fuse had multiple apertures, we looked at the aperture that was not looking at the star and that had a measurement of the diffuse background. So what you see is that you see a few bright regions. This is the Magellanic Clouds here, a very bright source. Here, this is the Coalsack Nebula here. This is the Lambda Ophiuchus complex. And so basically wherever there are bright stars, you see a bright diffuse signal. There's a lot of scattered light near bright stars. The surprise here is that we can look in the galactic plane, and even in the galactic plane, there's some very dark regions of UV. Even though you would expect the galactic plane to be bright, because there's a lot of there are a lot of hot stars, and because there's a lot of dust, it turns out that it's actually pretty faint in the Voyager range, and as I'll show in the next slide or two, in the Galax range also. So one shouldn't one can't assume the UV, or rather, let me say it this way: the UV sky is patchy enough that that one needs to look at a region in more detail to understand whether it's bright or not. And so here are the Galax images. Now Galax, because I had the all sky data, I have much better coverage of the sky. And so this on the top left is the far ultraviolet sky. And this is the near ultraviolet sky. And again, you can see, excuse me, you can see multiple effects here. At the very smallest scales, this bright patch right here is Spica. And Spica, of course, one of the brightest stars in the sky. And it turns out that, that it's got a halo extending out about 5 degrees from the star. There are a few others like this. This is a Kernar down here, and there's maybe a handful of others. But they have an extended halo around the star. And this is from a very small amount of dust that's scattering light at a large forwarding angle from that star. Here's the North Polar Spur here. You can just barely see it. The diffuse background is much brighter near the galactic plane. So this in the FUV, remember that the FUV didn't observe that much in the galactic plane because they didn't want to damage the detectors. And in the NUV, and again, there's some very dark regions or darker regions than you would expect even in the plane. The black here is where there's no data at all. You can also see that the plane is brighter than the poles. There's a typical cosecant drop off, which I'll show in a little bit. And the poles is actually very dark. And so if you're looking for extragalactic light, you can see the extragalactic light from the poles. Now, so those are the observations. So I have the Voyager data and I have the Galax data. And then I thought I would try to model these. Now the modeling is very straightforward. And again, the great advantage of the UV is that it's dark. There's just not many stars. If you're looking at the optical, you have all these red dwarfs these M stars that you can't avoid. But in the UV, there's only a few thousand stars that you have to worry about. And so what I did was I divided the galaxy into boxes. I took the stars from the Hipparcos catalog, that's 100,000 stars or so. I took the stellar spectra from Castelli and Cruz, and the stellar type from Hipparcos again. I assumed a dust distribution, and I'll show you the dust distribution in the next slide. The optical constants of the grains I took from Henye and Greenstein, and this is a 1947 paper where they more or less just derived, or they more or less assumed a parameterization of the dust, where you have the albedo, which is the reflectivity of the dust, anywhere from 0 to 1. And then you have a phase function scattering parameter, which goes from -1 to +1, where -1 is entirely backscattering, +1 is entirely forward scattering, and 0 is isotropic. Photon hits the grain, and there's an equal chance of it being scattered anywhere in the sky. Typically, we assume that from dust models, we know that the dust is moderately forward scattering, anywhere from G of 0.5, 0.6 or so. And we expect that the albedo in the optical is anywhere from, let's say, 0.2 to 0.6, depending on your wavelength. And so once I did this, then I just took a Monte Carlo procedure. I selected a star from the Hipparcos stars at random, emitted a photon in a random direction, went through each of the cells of my galaxy, and I stopped after specified optical depth, again, picked at random, was reached. Then the only trick here is that at every scattering, you take a little bit of the photon energy and say how much will hit your detector. And then you continue with your scattering until the photon energy drops to some level or the photon escapes your box. The stars are pretty easy. We know exactly where the stars are. Very hard to hide a bright star. So we know where the stars are, and there's not much uncertainty there. The dust is more difficult because you just don't know where the dust is. You don't know what you don't know the three-dimensional nature of the dust. So recently, people have used first the Pan-STARRS data. This is Greg Green, used the Pan-STARRS data, and now more recently, people are using Gaia data to derive dust maps for the galaxy. And so this is Greg Green's, I think, 2015 paper, where he has the dust distribution as a three-dimensional dust distribution. And so we used his dust distribution. We filled in the holes using using an empirical method, and that gave us the dust distribution. And then we used the stars, and so now we have everything we need for our dust model. And so what we get in a robust manner, again, I want to emphasize that the dust is uncertain. And many of our effects are all local effects, and we have a hard time understanding the dust at very local distances, if we're looking within a few parsecs or within a few tens of parsecs of a star. So if I look at any particular reason, my conclusions are suspect. But as an overall picture, these are pretty robust. So I'll just give you a few of the highlights of the modeling. One is that 80% of the diffuse background in the sky comes from only 1,000 stars. 60% comes from only 100 stars. And the top 5 stars give you 6, 8, 10, about 10 to 15% of the background is from only 5 stars in the sky. So it really is a very few number of stars, and the effects are largely local. And this is emphasize, but if you look at the point of scattering, where does the scatter, when we look at the diffuse background across the sky, where does it originate? And if I'm looking at the UV, the optical depth of the dust gets to 1 within a few hundred parsecs of the sun, 300, 400, maybe 500 parsecs. And so most of the scattering that I see is within 600 parsecs of the sun, even with a lot of it being even within 200 parsecs of the sun. So again, it's a local effect. So even if I look at, let's say, the galactic center, which I can do, I do have diffuse observations near the galactic center, I won't see to the galactic center. I'm really looking at the local line of sight at the nearest 200 to 300 parsecs to the galactic center. And so I can put all of this together and I can get models of the sky. I won't go into the models. The red stars here are, that's basically Gould's belt. It's the bright TD1 stars. All right, so now if I go back to my data, if I look at the data, you can look at the dependence from the galaxy, dependence on galactic latitude, and essentially you get the cosecant dependence that you would get for anything that depends on the galaxy. So what does this tell you? This tells you that most of the diffuse background is most likely from interstellar dust scattering. As you go to the poles, you get a residual of about 300 of our photon units. And I'll talk about that a little later. And this has been the case since the early observations. People have observed a diffuse background of 200 to 300 photon units. Now we're pretty sure it's about 300 photon units at the galactic poles. In the early days, they thought maybe this was all scattered from galactic plane dust. And so Mike Jura, who did the first of the models, he said, okay, so that tells you that the dust has to be isotropically scattering. You're getting stars from the galactic plane, the light goes up to the stars and is scattered back to us. So therefore the dust is isotropically scattering. Now we know from dust models that it's not isotropically scattering. And so the actual scattered light from dust is only a small part of the total. Here I'm just plotting the Voyager observations. And again, you can see the cosecant dependence, but the center near the galactic plane is filled in. And a lot of that is because as you go further and further into the UV, your optical depth becomes greater and greater. And so you're looking to shorter and shorter distances. And so you're starting to see a lot more local effects. If you're looking only 100 or 200 parsecs away from the sun, you're likely to see a lot less of these galactic effects. And so my last few slides, I'll talk about the work we've been doing at the poles. And the poles are interesting because that's where you would expect to see the most extragalactic signal. You get the least amount of dust. This is the I lost that. This is the IRAS 100 micron map, and this is the Planck dust map. And so you get a very low amount of dust there. The EB minus V is typically 0.02, 0.03. And you might expect to see the greatest amount of extragalactic light because you don't get much scattered light from the galaxy and you don't get much extinction of galactic light. And so here is the FUV map and the NUV map of the polar region. And so the things to just see as a morphological description, as a science by eye description, is that you see these dust clouds in the infrared and in the Planck data. And so this here is a cloud that's known from polarization. And you can see these other cirrus features here. You can see them in the FUV. So here's the same cloud here. Here is, again, you can see the feature, but you don't see it in the NUV at all. And this was a bit of a surprise to us because if you see a dust feature in the FUV, you would expect to see it in the NUV. And so our explanation for this is that what we're really observing is molecular hydrogen fluorescence. In the FUV channel, you get the, I think I always get them mixed up, but I think it's the Lyman bands of molecular hydrogen. And that we think is what we're seeing. So normally you think of molecular hydrogen forming at higher densities because they don't form until the density is high enough for self-shielding. But here, they're actually forming at fairly low column densities, at a column density of about 10 to the 20 or so. And the rest of what you see is largely extragalactic light. And so this is our model here. If we look at, this is the FUV on the left and the NUV on the right. And so here are our observations as a function of EB minus V. And so if you look, you can convince yourself, and actually it does hold up statistically, that there's a bend in the curve, an elbow in the curve at about an EB minus V of about 0.03. And so here it's more or less flat, and here we get a bend in the FUV. And this is what we're attributing to molecular hydrogen in the fluorescence bands of molecular hydrogen. In the NUV, there's no such band, and you wouldn't expect one in the band because you don't get any molecular hydrogen in the NUV. And this part of the blue plus signs are what we expect from dust emission from our modeling. And the green is if we take up all of the extragalactic light together and add all of the different components together, we get this green. So we take the blue and the green, we add them together, and we're short of the observed signal. And so what we get is that we observe something on the order of 250 to 300 photon units in the NGP and the FUV, about 500 photon units in the NUV. Of that, the extragalactic light is 100 photon units in the FUV and 200 in the NUV. And so that leaves this remainder, 174 in the FUV, this is in the NGP, 130 in the SGP, and about 300 to 400 at in the NUV. And this part we have no sources for. Sri Kulkarni has just done a census now, and he's done calculations. So he says he can explain about maybe 1/2 to 2/3 of this, particularly in the FUV. What he says is that 2 photon emission from the heliosphere is important, but that we still have to see. Yeah. So that's my final conclusion on the UV. This is more or less where we stand now. What I'm doing is I'm doing a couple of other things. We see this offset. I'm trying to see if this offset has any latitude dependence, any longitude dependence, all stuff that we're just doing. I like working with data, so I'm primarily observational, primarily data oriented. So rather than worry about the source, I'm just seeing if I can characterize its behavior. So that's one thing. The second thing is that I see a time variation in the diffuse background. Now, it's hard to understand what a time variation would be if it's except something from the Earth's atmosphere. But again, that's something that I'm working on, and hopefully I'll have results soon. But let me just close out my talk with the diffuse optical background. And this is interesting. Of course, I mean, the background in any wavelength range, as Petri and Calevi know, is important. And so the diffuse optical background, people have tried from the ground for years. Very difficult thing, because you're competing against so many things. You're competing against the sun, against the atmosphere. You're competing against the zodiacal light, and local effects matter. So it becomes difficult. So what you would like to do is you would like to go outside the solar system. And so there have only been a handful of probes that have gone out the solar system. Here is Pioneer over here. This is Pioneer 10, Pioneer 11, and Voyager 1 and 2. I think Voyager 1 is some 20 light minutes away from the sun now, if I remember right. And so so as you go further out, of course, you get rid of the atmospheric effects, but also you get rid of the solar system effects. And so this is from New Horizons, and it's a map of the Lyman alpha emission, which is resonantly scattered Lyman alpha. It's solar Lyman alpha, resonantly scattered from interplanetary hydrogen. And as you go further out from the sun, the level drops. And so now for New Horizons, it's pretty much at an exponential level. It's pretty much plateaued at a low level. And so you would like to do this for the optical also. And so what Gary Toller did is he took the Pioneer data, tried to subtract the stars from it, and then tried to map the diffuse background. This was a difficult thing because Pioneer was not made for that. But anyway, this is the observations he got. And now people have used the LORRI instrument on New Horizons to do the same thing. So I'm not going to talk much about the background. I'm just except to tell you that that it's happening. And so here is a set of observations of the diffuse background over the entire wavelength range from the let's see, cosmic microwave background over here, over to the infrared background, the optical background, the UV background, which is the stuff that I'm talking about here, and then so on down. So we find nothing very, it's already low here, and we find levels at more or less this same level. We're just trying to pin it down more. So let me close by just telling you what we're trying to do now. So we're trying to use New Horizons. New Horizons is now well past Pluto. They're trying to look at more Kepler belt objects. But again, while they're doing that, they have calibration observations, and they're going to try to take a few science observations. And so what we would like them to do is we would like them to take some long observations at the galactic poles, as long as makes sense, maybe a few, maybe 10,000 seconds, maybe 20,000 seconds, and just to see what we get. We can combine the LORRI data, which the galactic poles have very few stars, so you can get good measurements of the optical background. And we use ALICE to measure the diffuse UV background. And again, just see what we get. See how good the limits are that we can place on the background. Then one of the things that I've been trying to get people interested in, but always difficult, is the idea of putting an FUV imager with high spatial resolution on the moon. If you're at the moon, you avoid all of the air glow. You avoid almost all of the solar system, right? If Shri is correct, you might still see the 2-photon emission, but you avoid most of the background light. The sky in the FUV between about 1300 and 1800 angstroms is truly dark. There's no local emission, or at least very little local emission. So if you put an FUV imager on the moon and just let it observe for as long as you want, you get a chance to really pin down the galactic, and if you look at near the poles, the extragalactic background. And the last thing I'll mention is an instrument that we're planning to put on the Chinese space station. So a couple of years ago, we had there was a proposal call from the United Nations Office of Outer Space Affairs, UNOSA, to put an instrument on the Chinese space station. And so we proposed, and we were one of the science experiments accepted. There's a much better one from the European, I've forgotten what it's called, I think Polar, a much better gamma ray experiment, but we put it up. So we're doing this purely with local resources. And so the total cost of this experiment is maybe $10,000, which, if you can imagine, for a space experiment is tiny. Hopefully geopolitical considerations won't affect us. I mean, we're all members of BRICS, but sometimes it doesn't feel that way. And we should be launching on the Chinese space station in the beginning of 2023, or maybe we have to deliver to them by the end of 2022, so sometime in 2023. So again, this is unheard of for a space mission to complete the entire thing within about a year. Of course, we're doing everything we're not using space qualified material, we're using mill grade material, where we don't have all the redundancy, and it's a small instrument. But nevertheless, we do think that this is an exciting way to do science, that there are opportunities opening up. Hopefully more will open up in the future. And so if we can build these small payloads and take advantage of these opportunities, we think that you can do at least niche science with that. So let me end there, and happy to take as many questions as you'd like.
Thank you, Professor Murthy. It was really great journey to the UV background. In fact, David has asked one question on chat box. I will just read that. Is there any additional information on diffuse emission from EUV instrument like EUVE?
No, there isn't. And part of the reason is because we just don't see deep enough. You're lucky to see out of our solar system in the EUVE. I mean, I know they saw a few stars, but no, there's not. They placed limits on the interstellar medium by looking at the EUVE signal from that, and from CHIPS also, which also looked at the EUVE, but no diffuse observations.
Okay. There is one hand raised. Please ask question. I can't see the name. Okay. Anyone else, please unmute and ask question yourself.
You can ask Petri and Kalevi if I missed anything out.
Yeah, Kalevi, thanks for joining from Finland as well. Yeah, I just have a brief question, just from your. I mean, first of all, my hat off this, having dabbled in this area some time ago. It's just so difficult when you're dealing with measurements right at your detector noise, or just in principle the faintness of everything. It's just extraordinary that you're getting results. So excellent work. And just on a, one of the things that I don't personally know very much about at all is Zodiacal Light, for example. So from your perspective in the UV, is there anything you feel that there's unknown on the on the interplanetary side of things when you're trying to subtract the background? And of course, I know that Kalevi would know more about this, but specifically from the UV perspective, or is that not an issue at all?
Well, firstly, let me have a mutual praising society. Let me return your compliment by saying that the work that you do on the diffuse optical light is much more difficult. But the Zodiacal Light, no, there's not that much that we don't know from an empirical point of view in the UV. We understand it pretty well, because it follows the optical maps, and the optical maps are certainly good enough for our observations. So no, I don't need to know much more. In the infrared, of course, it gets to be more difficult because then they have all those striations and time-dependent effects. But I don't think we have much of that.
Okay, and would you have any guesses? This is now going to the whole of the backgrounds, both optical and the things that you mentioned there of kind of the unexplained. Do you have any wild guesses of what could be? This is something that we found as well.
Yeah.
In the optical, there are, when you compare galaxy counts and the measurements, there's still something there. What do you have your personal favorites of what the wild
no, Petri, I mean, this is something that, as you say, you see it in every wavelength. You see it in the cosmic infrared background, optical background, the UV background, this unexplained component at the poles. And so we'll go out on a limb and say it's dark matter. Everything is dark matter.
Can you hear me? Am I on the line or not?
Yes.
You can hear me. Yeah, I'm Kalevi Mattila here. Maybe we have a speaker from rather far away, but also somebody, myself in the audience, in the other direction far away. It's very pleasant and nice to see you, Jayant, if not at the Commission 21 meeting anymore, because that has been abolished, so at least in Zoom. Now, not going longer on that, to continue what Petri asked, one more question about this unexplained, or let's say about the UV component at the poles. Now, of course, I have seen your paper on that, but how is it with the 200 up to 400 units left over, so to say, for the EPL or maybe unexplained? How much of that is explained by the known galaxy numbers, if you add up what you expect in the UV from all the galaxies? Is there an unknown component?
No, we subtracted whatever the calculations are. Using the galaxy evolution, using quasars, we subtracted all of that off. And so this is at least 1/3 of the signal is something we don't know.
Yeah, so that's very satisfying in the sense, not in the sense that everything agrees nicely one-to-one, but it's very nice as long as you have something unexplained, because that's the exciting thing. And I know you and Dick Henry have been advocating also some very exotic physical processes to explain this unexplained, let's say, maybe extragalactic or maybe partly galactic component. Okay, not going longer on that. About the New Horizons is, of course, a very promising, let's say, new experiment, new in the sense that took a long time to get out there, but a new experiment compared with a long history of the light of the night sky studies. So your new plans you mentioned at the end, that's in the optical now. You with the New Horizons LORRI experiment, you really get to the as far away from all the disturbances near the Earth and in the especially the Zodiacal Light. Have you got really an approved program there? That would be exciting, because I know it's so strongly concentrated on the planetary system, or these Pluto-like objects or smaller solar system objects, that they need so much time for transferring the data, not actually getting it, but to transfer it back to the Earth, and you are competing for that time. But did you get something in progress there, or is it that wishful thinking?
So I can tell you what the status is. We have, of course, the LORRI people are doing their own things, and they've got some good results. You must have seen their results.
I know the latest by Lauer et al. Yes,
exactly. So what we have, what I have are the ALICE observations that were taken at more or less the calibration observations. And so I haven't published them yet for a couple of reasons. One is that they don't add that much. And the second is because the New Horizons people, they're a little sensitive with publications. So,
Yeah.
so that anyway, the data are promising, but maybe as we get further out, as we add more data in, they'll get better. So what they've done is that they've submitted a proposal to NASA for an extended New Horizons mission. And hopefully that seems to be, it seems to have a decent chance. And part of that mission is to look at the background, in the UV background and the optical background. So I think there's a reasonable chance that we will get data. We are getting data anyway, because they're continuing with these calibration observations. And so we are continuing to get data from way out in the solar system.
Okay, thank you. Another question related to that, Lori, as you get further and further out of from the sun. Now there was a point, I think Petri mentioned that, is there anything unknown about the zodiacal light? So I think there has been still continuing the question of an isotropic component of the zodiacal dust, scattered light or whatever, scattered light principally in different, in the optical, I have read about that, maybe in near infrared. Is there in the UV any question about having an isotropic component of the zodiacal light, which would be even more difficult to get rid of, rather than the one which is dependent on the ecliptic latitude?
Because the advantage of ALICE is that we get down to 912 angstroms. So ALICE is 912 to 1500. So we just won't see the zodiacal light.
Okay, that's away anyway. Yeah.
Okay, maybe we can take a question from David now.
Yeah, they're sort of engineering technical questions, Jayant. The first one was regarding I think it was the NUV on UVIT. What was the cause of the failure of that? And the second one was, do you foresee any advances in detector technology for UV astronomy? My sort of rather ill-informed knowledge about this is many of these detectors, you mentioned Aussie Sigmund and so on, they all have still these sensitive image intensifiers like microchannel plates and so on, which are subject to being overexposed. And do you see anything on the horizon in terms of advances in the technology?
So the first question about UVIT, I haven't seen any convincing explanation of why the FUV detector was failing earlier and why the NUV detector has failed now. They're old detectors, and so who knows? But as far as advances in detector technology, there's a few things that are going on. One is this thing coming out of JPL, these delta doped detectors, where they're saying efficiencies of 40 or 50% in the UV as opposed to our 10%. So you get a significant factor right there. Right now, Ultrasat, which is this Israeli-German collaboration to look for variable sources. I mean, you must be aware of that. They're using some sort of detectors from DESY, from DESY in Germany. And I don't know the technology there. We have a collaboration with the Tübingen group, Sebastian Diebold now. It used to be Klaus Werner. Now Sebastian Diebold has taken over. And they're using this gallium nitrate detector, which again gives an efficiency of 40% all the way from 900 to 1800 angstroms. So over the next decade, certainly the detector efficiencies have improved by a factor of 4 at least.
Right, thanks.
None have flown as yet.
Yeah.
I think now we can take a last question from Sri Ram Sankar. Can you please ask your question yourself?
Hi. So I have a kind of a naive question, I think. So I used to work in QS of light spectroscopy, for which we use UV background, as you probably had. And we use all these KS8, KS20, FG20, Hartman metal backgrounds, and all these things. So they are a function of redshift. So how does this relate to that particular background?
So when they calculate the extragalactic background, what they do is that they take galaxy evolution models, they take quasars, and they just add everything up. The observational limits have come from places like, I think it was Virgo, where they looked at the deep end of the galaxy function. You see where you count galaxies and you see where they turn over. And so typically they say it's about 100 photon units if you add everything together. Of course, we're looking down at the far UV, we're looking down at 1500 angstroms. So yeah, so that's about all I could say. I don't know if I answered your question at all, but that's all I can say.
Thanks. It's really interesting. I learned a lot today.
Okay, then it was really nice to have you, Professor Murthy, in our session. It was really nice talk and very nice discussion afterward. Thank you. Thanks a lot for accepting our invitation.
My pleasure, Sunil.